Hey everyone, and this talk will be about distributed computing workflows on big data with FugueSQL. So Fugue is a open source framework that I've been involved with, uh, and for the last couple of months. But we make sure to cover the basics of distributed computing as we give this talk, just so people understand the motivation and the concepts behind what we're doing. So I normally give this talk with Han Wang, uh, and to introduce ourselves, I mean, well, he's not here, but to introduce myself, um, I am currently an open source community engineer at Prefect. I changed job 2 months ago, 2 weeks ago. I was right now I am more on implementation and data orchestration, those kinds of stuff. But I was a data scientist for 4 years. And my last job, I was working at a company called Paylocity that does payroll, and we did HR applications. Like, for example, we did stuff like predicting time and labor, or like predicting employees that were like at risk of leaving our like clients' companies through their payroll data. Like we would see stuff like, oh, who hasn't been promoted in a while, who is getting less hours, like stuff, and those were like predictors to see who would be at risk of leaving. I was also a mentor for a data science boot camp called Thinkful, and I also organized the Orlando Machine Learning and Data Science meetup. Good to see some common members between these two meetups. And Han, who I normally give the presentation with, is a tech lead of the Lyft machine learning platform. He is the founder of the project, and he has experience with big data across a various number of companies. So this talk was originally given for bootcamp students, and so some of these slides will be about like where exactly Fugue fits in. What's the current tooling uh, in the data ecosystem, and where exactly Fugue fits there. So normally when you go to a data science bootcamp, some of them start out with Excel, and then they proceed to Tableau, and then some variation of like SQL and Python. For data analysts, they primarily focus on the SQL Tableau portion, and for data scientists, of course, more on the Python portion. But of course, the landscape for of tooling for data professionals is like uh, they're getting bigger and bigger. So first you start off with Python, and then you graduate onto Pandas. And on the SQL side, which I personally find interesting, is we're seeing this trend of SQL uh, tools being based on SQL that let you do other things. Like for example, like Tableau, right? Combined and Power BI, you can have a SQL layer uh, to have between your reports and your database, so that you can do like you can use the SQL to pipe in report for your reporting purposes. We also have stuff like DBT, which is getting a lot of attention recently, where you can use you can use SQL to control your data pipelines. So DBT allows you to use SQL to query all of these different data sources, and it has adapters to those data sources. And then you can join the tables once they're loaded in DBT, and then you can save those outputs also. So also for like reporting data pipelines. And then of course we have BigQuery, which and Athena. And the reason I list these two is because they allow people who are very familiar with SQL to use SQL to analyze a CSV, so that they don't have to move to Python, right? So if you just want like an ad hoc analysis, you can spin up AWS Athena, and it you run SQL queries on the fly on your flat files. So we're seeing SQL now being used for more than just loading in data from a database. But of course, like as when we start out with Python pandas, but as the size of data is getting bigger, we see more and more tools that are specialized to handle big data use cases. On the Python side, we have Spark, we have Dask, and these are distributed compute frameworks that are capable of, uh, you know, like handling in the hundreds of gigabytes to terabytes of data, because Panda starts to break past, I don't know, let's say 10, 20 gigs. And then on the SQL side, we see more like we see these data warehouse systems like Redshift, like Snowflake, also SQL based. And then we see Presto, Hive. So Hive is also has its own querying language, wherein you can use that that SQL-ish querying language to perform MapReduce operations on data with the Hadoop like big data like storage. And then we have Presto, again, similar to DBT, where you have a ton of connections also to a lot of different databases and a lot of different like storage. And then you can combine and make reports. So we see that there's this trend on the SQL side, which is really interesting, where the tools are adapting to the SQL users. So we have people who really know SQL. How do we get like how do we adjust the tool to fit their needs? But on the Python side, it's quite different, right? It's like we have Python, and then you have Pandas, an entirely new framework on top of Python, and then you have Spark and Dask. Although Dask and Pandas share some similarities, there's also quite a lot that you have to learn in order to start using these frameworks. Same with Spark. Spark and Pandas syntax, as we'll see in a bit, is completely different. They have a different family of functions also and utilities. So here's a sample code snippet of Pandas and Spark. And in Pandas, if this were the syntax, um, it's an entirely different syntax in Spark, right? And the purpose of showing this is that we don't realize it, but the way we code is very coupled with the framework, right? If you write Pandas code will not run on Spark. You write Spark code, that Spark code will not run on Pandas, right? And the issue is that we find ourselves as a data professional, we find ourselves in some situations where maybe the data starts out small, like 5, 10 gigs, and fits in Pandas. But then as you collect more and more data, you start to graduate beyond the capabilities of Pandas. And then now you need to move to Spark. And over a big code base, this requires significant amount of changes, practically a whole rewrite, right? So the motivation of Fugue is how can we get, well, there's two motivate, well, the first motivation of Fugue is how can we have a framework that adapts to the users to have them code in what they're comfortable in, and then they can choose an execution engine to run that if they want to run it on Spark or Dask. So we want to decouple the expression of logic versus the actual execution side. Uh, and that's what Fugue is. Fugue is an abstraction layer that lets you code in native Python or in SQL, and or a mix between the two. Sometimes mixing them provides a more powerful combination, as we'll see in the notebook. And then as the abstraction layer is the one that will adjust the code to the frameworks. So it gets the Python code and the SQL code, and then it maps it to Pandas, to Spark, or Dask. So now you can use the same code and swap the execution engine under the hood, and then you can you don't have to change anything, uh, even if the size of the data increases. So for my previous job, like for example, you had some utility functions. Like for example, we cleaned this particular set of data this way, right? And that set of data would sometimes exist in Pandas workflows and sometimes exist in Spark workflows. And you would need to write that cleaning function twice, one for each implementation. But with Fugue, since the logic is decoupled, you can just write that function once, and then you can choose the execution engine to run it on. So here are the goals of Fugue. Number one, want to eliminate the need for people to adjust to frameworks. We don't believe that frameworks should hijack a project and force you to code in that framework. And even with Fugue itself, we want the if you want to use Fugue, we want the onboarding process to be easy. But if you want to decouple your code from Fugue, we want the offboarding to be easy as well. Number two, we want to allow people to express their logic in the tools they prefer. And this can be Python or SQL. And then number three, because this is motivated by big data and distributed computing, we want a tool that is agnostic to the size of the data, that allows users to not worry about that and let the execution engine adapt to the volume of data. So Fugue has two interfaces. One is the programming interface, Python based. The second one is the Fugue SQL interface, which is of course SQL based. The reason I give this talk in SQL is because number one, we just have like better feedback on the SQL portion, but like the Python one is a bit trickier to use, and you'll see later that maybe in some cases SQL is indeed the better abstraction to deal with data. And number two, in general, it's like easier for people just coming into like people who are very versed in Spark and very versed in Pandas already, like they will not use a new framework because they're already comfortable there. So we need something that we want this to be introductory to people who haven't yet hit big data, but we want them to be able to use big data easily. And that's why we give this talk in SQL. So just to clarify when Fugue SQL is used, number one, it's not for database querying, it's for querying flat files. So it's like Pandas, you load in a CSV, you do some transformations, some analysis, output some plots. This is what FugueSQL is for. It's for working with flat files and in-memory data frames, not for database querying. Number two, we have an extension with Jupyter Notebook that really enhances the experience, and I'll show that later. So you can use SQL on Jupyter uh, on top of Pandas Spark or Dask DataFrames. And number three, we can parallelize operations or use the speed up available by going to Spark or Dask. And I'll check the chat.
Yeah, so we have one
Yeah,
question talking about if there are size cutoffs between doing something locally with pandas or going up to the larger scales.
yeah. The answer is you specify. And in general, I don't think there's a hard cutoff that's like, oh, I need to use Dask. Um, so uh, something about Dask is that something about Pandas is that the author of Pandas himself said that if you want to, to be performant, you need like I've seen different numbers. I've not heard the first-hand source, but I've heard 3 or 5 times the amount of RAM as your data set, right? So if my data set is 8 gigs, in theory, I need 24 gigs to remain for Pandas to remain performant, right? Because Pandas was made in 2010, and um, like back then, the volume of data was not as big, so Pandas by design was not meant to handle the loads of data that we are seeing today. Um, and that's why even if your data set is around like 5-6 gig, you may see gains by moving to Dask. But to answer your question, no, it's something you have to specify. You choose what engine you want. Okay, so the goal of this workshop, or not really a workshop, it's a workshop for the bootcamp students, but for us, it's just a just really a talk. One will introduce end-to-end. Will introduce the distributed computing concepts, and number two will introduce FugueSQL as a way to perform end-to-end compute. Okay, I have some links here. They're also in the notebook anyway, so I should just hand you guys the notebook. So the notebook is here, and I will put this in the chat. I should say that the notebook may be just a bit different from what I'm gonna present because I was making last minute edits. If you click the link, you're gonna see the last working version. So there may be some slight differences. Number two, the uh, no, actually, no, never mind. No number two. So yeah, there may be some slight differences. Also, the links that I showed are up here at the top. So if you want to take a look at the repo, which is over here, or if you want to join our Slack channel, and you can join our Slack channel. You just want to talk more about Spark, Dask, distributed computing, what's wrong, what the pitfalls of it are. Um, of course, we hope you use Fugue, but we think that as you find yourself find the difficulties of using Spark and Dask, then you'll see Fugue as a viable alternative. But anyway, let's get started. So um, over here, we just have the Fugue repo and Slack links. And then I got this, we're dealing with Instacart data today. And there was a competition 4 years ago. And I got um, a lot of the plots that I used in this demo. I copied from this notebook. So just giving credit. So first installation, we have this package called Fugle, which is just Fugue plus Kaggle. So there's some optimizations uh, specific for the Kaggle setting, but in general, you would just do pip install Fugue. It's available via PyPy. And then now we can run this setup command. So from Fugle import setup, and then the last sorry, my pressure cooker. And then the last thing is the data came in all zip files. So I'm just gonna unzip everything so that I can use it. So the first the first thing about Fugue SQL is that there are enhancements that went into it over traditional SQL. So the first example is loading and saving, right? So if we want SQL to be capable of loading in date, like handling end-to-end like ETL pipelines, then we need to be able to load and save data. So we have the load command and the save command. And you'll notice that this is a Python cell, but we are using this cell magic to run the cell in SQL, right? I mean, to have the Fugue SQL on top, and then the Fugue SQL is mapped into the corresponding Python frameworks. So first here, we just have a df equals load, and then header true in first schema is true. In first schema is a Fugue a Fugue addition, just because like, for example, if you have CSVs and you load it in Pandas, it normally just says everything is a string. So we want to infer schema. Um, and then we can do select star from df where lid equals 3 print, and then save overwrite. So this prints this command. This save overwrite is also applied to this command. So this is our output, and that's what we're saving. So in general, all of the ANSI SQL keywords will be available in Fugue SQL. So here's another simple example. What we're going to do is just load this data frame, um, select the department So I'm just gonna print 5 rows of the um, data frame just so we see what we're working with. So we have the product ID, product name, aisle ID, and department ID. And this query is just getting how many products are in each department. Uh, and I'm just putting a random filter just to show. And then we have our group by and then print. So here is the out, and this current. So if you don't specify an engine, and we'll show that later, everything is done in Pandas. So these are Pandas data frames, and we um we did our group by, and we're just showing the count. So this is the count and the group by. Uh, okay. So because this is a Python meetup, I just added some like what the equivalent syntax would be in Python for those like for that group by and filter. So here we're going to read the CSV. I have to convert the type to integer so that I can use the loc like this. So loc is our filter. And then instead of doing this group by count. I'm instead just going to use the pandas value counts, reset the index, change the column name, and then we end up with the same thing. So over here, you can already see that, I mean, there are some people who just prefer SQL as like in terms of like readability. Um, Also, I should note that we allow for variable assignment. So that's like, I think that there's a section about that later. So we'll just talk about it later. The second thing I'm going to show is we just walked through the pandas implementation. Next, I'm going to show what does the Spark implementation look like. So for those who have not seen Spark code before, we can see how different they are. And here I'm going to import the Spark session, instantiate it, and then read it like this. And then we do our filter, group by this, and then aggregate and the count. So it's very readable, but in a in a large code base, you could see how these two would definitely diverge over time. Okay, so the rest are just like simple additions that we had to FugueSQL. So number one, we have alter columns, and this takes in this df, and then we just alter the columns. So this is the same as pandas as type. So here we are changing IL to int and IL to string. Uh, a schema can be inferred also. Schema can also be changed during loading with the syntax, right? So load and then these columns, here you'd specify the schema. There is also interoperability between Pandas DataFrames and the FugueSQL, right? So here I am going to make a new data. This is a Panda cell. I'm gonna get a new data frame by loading in this file, and then I'm gonna make a new column, right? One, just so we see it later, and then I print the head. And over here, this test is the same as this data frame. So now I can do select star from test, print 5 rows, right? So this is the same as this. We can also do the opposite operation, where if we worked on something with SQL, we can pass it out to pandas, right, to continue working on it if there were some transformation that you wanted there. So here we load, and then we select star from df where I'll equals 3, and yield is the keyword that puts it out into succeeding SQL cells or with Pand or with normal Python. So here, this result, we yielded this data frame as result. So now we can print. This is how we would use it in pandas. Result as pandas, and then we get the head. And this is the same as this. Similarly, this result here is available because of the previous yield. So now we can do select star from result, and we get the same one. I think Jinja templating is the last thing in the introduction. So Jinja templating is how can we use a variable, a Python variable inside the SQL query, right? So here we have a string, and then I can do select star from df where I'll equals, and I insert this variable inside here. And that's how I get specialty cheeses in the aisle section. Oh, I guess the last one, anonymity and inline statements. So anonymity is we don't need to specify if there is no data frame specified, then it automatically gets the last data frame that was worked on, right? So print is the best example of this. We actually have a syntax that's like print 5 rows from df if you don't want the previous data frame. But if you don't specify a data frame, it just prints whatever the last one was. Alter columns also has from df, but since we don't specify, it just both of these automatically just run on df. So the hope here is that FugueSQL is more English-like, a bit like cleaner to use also, and this can simplify your SQL code. The next portion is data analysis. So if there's any questions uh, on the intro, now would be a good time. I'll give it a couple seconds. Okay, so moving on, um, we're gonna show these are uh, Python functions, and I have these are all just seaborn plots if you're familiar. So in general, I'm gonna make a new plot. I'm gonna put a seaborn plot inside, change the labels and the titles, and then show the plot. And I'm just making a bunch of these helper plots. They all take in a data frame. They'll plot some certain column, uh, and we're gonna use them inside the SQL. So before that, we're gonna look at what data we're working with. So I said this was Instacart data. This was a competition where you have to predict what the user will buy in the future, given their history. This was 2017 data or something like that. So first, we'll get the orders table, um, and we'll print 10 rows from it. Here you can see we have an order ID, a user ID, the order number, and then day of week, hour of day, and the day since the prior order. And then we'll do order products. I only got these, I dropped one column that was not too useful. So here is what we have. We have the order ID, the product ID, and whether or not it was reordered. And these two are our main tables that everything joins to. Um, there, the thing you should note is this yield file, right? So, and the programming interface has this also. So yield data frame puts the data frame in memory. Yield file allows disorders to be used in succeeding data frames, but it's saved in a temporary file first. So when it's called upon in the future Python code or SQL code, it's going to load from that temporary file uh, on like when it's needed, right? And this is important. This is like a sort of like a caching in distributed computing. So first we are gonna go through the count of like how much data do we have, and I chose this data set specifically because the size of data is quite big, where we start to see performance gains if we switch to Spark or Dask. So the orders table is around 3.4 million rows. The count of the order product, so it's like the order products is like order one, order two, order one, product two. So all of the products and what orders they were part of, that is 32 million rows. So quite big. So here's an example of an operation that is kind of uh, long to write in SQL, and I'm going to see the number of missing values uh, in in the data frame. So I'm doing it on the orders data frame, and you see it's quite cumbersome to write out in SQL. This will work though. I did get a value because it doesn't. This is count everything and then count the non-nulls and then we subtract. But of course, Pandas has a much easier function. So I'm going to make a new function here, and I'm going to take in a data frame and just get get the null counts of each column and then return that. And now I can show that I'm going to use this. I'm transforming this data frame using this Python function, right? And same thing, because I have this general function, I can also transform the order products table using this Python function. And the order products table has no null values. This one has a bunch of nulls, the day since prior order, because if it's the first order, this will be null. So everything makes sense. Otherwise, we're not missing data. Uh, if there are any questions uh, in the chat before we discuss a bit of distributed computing. Okay. So before we do further analysis on the data, we're gonna just talk briefly about distributed computing. So uh, if you're not familiar, the main two frameworks right now in with Python are Spark and Dask. So the Dask repository, I got this diagram from one of the issues there, and it's a pretty nice summary of distributed computing, right? So you have a client or master or just something that orchestrates everything, and this is the thing you're interacting with, and you give your commands there, and then it uses the scheduler to manage the state, and then it also sends the task to the workers for execution, right? And then the workers are just different machines that have maybe there's data that lives in those machines. Sometimes you'll have to move data around, uh, and sometimes the workers will have to shuffle data between themselves. And this these workers plus the client, that's like what you call the cluster, right? So Spark and DAS achieve these differently, but essentially this is the same thing. So the cluster is a bunch of networked workers that are able to like serialize data and pass them around around each other, and you are controlling stuff through the client. So of course there's like we'll see later, but there's some stuff that doesn't translate well from Pandas to the distributed computing setting. Like example number one is like having an index, right? Like the index is like uh, always like maintained, like there's an order maintained to your data frame, but in distributed computing, that order is not like a global order, right? Normally we have orders for each worker, right? And it's not um, it's not a trivial thing to uh, sort everything in the distributed setting. So we'll start with analysis. Here, just simple, these are just some simple, just to show the plotting capabilities or the integration with Python plots. Um, so we're gonna have a temp df, and here we're just asking uh, what what the maximum order number is for each user. So how many orders does a user have? And we name that the n orders. And this is what it looks like. And then we select we want to build a histogram of these order counts. So we count the n orders, and then we output using this function defined earlier. And this is our output. So majority of people just used Instacart here in the low, like 4, 5, 6 times. And of course, it just steadily decreases. There's a spike at the 100, presumably because the data was capped or something at 100. And then because of our anonymity that we described earlier, we can also do this select star from orders, output using this first, then output using this, then output using this. So the first one is the day of week count plot. Um, the the day of the week labels were not given. Presumably 0 and 1 might be the weekend, Saturday, Sunday, where maybe more people do grocery. I don't know. But anyway, we see a spike at 0 and 1. Number two is hour of day. We see spikes around the the working hours. Uh, that's no surprise. And then frequency of uh, the days the days since prior order. So you're gonna see there's an interesting trend here where you're gonna see a spike at 7 days, right? So these are the people who order weekly, and then you're gonna see another spike at the 14 days over here. So like bi-weekly orders, and then there's a bit of a spike again at the 21 days. So people who order every 3 weeks, right? And then I assume this was capped again. So uh, here we're interested in uh, how many like how, how many individual product orders are actually reorders, right? So we do we make a temporary data frame, and the temporary data frame will contain the count of all. So this is the total number of product orders, and then we sum when reordered is 1, then 1, else 0 as reordered. So now we can just divide reordered over total, and we multiply it by 100, make it a nice percent, and we just selected from this temp data frame. So that gives us this. We have 59% of products are reorders. And then maybe we're also interested in how many orders have no reordered products whatsoever. Somebody came in and everything in their basket they're trying for the first time, right? So here we select order ID, and the if we group by order ID and we do the max reordered, if if at least one product is reordered, then it's gonna be one. If no product is reordered, then the max will be zero, right? So then we can identify which orders have reordered product items versus which orders have no reordered uh, items whatsoever. So we call this contains reorder, and then we can just do again similar to before. This is just the average will be will be a percentage of um, the orders that contain a reordered item, and then we just do like we multiply by 100, 100 minus this. So we have 12% of orders have no reordered products whatsoever. And then we're gonna show just a bunch of other tables that were given in this data set that we might be interested in. So number one is the products. We have product ID, product name, aisle ID, department ID. This obviously joins to aisle ID, which has an aisle name. And then same thing, we have department ID and department. So notice that yield data frame, again, keeps stuff in memory. So I only do it for the smaller tables. For the larger tables, I yield file so that we save it in a temporary location and then we'll load it later on. But because I'm yielding these already, all of these three products, aisles, and departments, you're gonna see me just call them like they already exist in the future FugueSQL cells. So now we have our order products table, and it was the 32.4 million rows or so, and we want to join these products, these aisles, these departments to it, so that we can do like analysis on the whole thing. And here's the first instance where I'm gonna just change the underlying engine where this runs on. So before I used Dask, I was running into memory issues, right? Like I was Python pandas out of memory. But one of the cool things about Dask is that if you're reaching your memory limitations, Dask can intelligently write to disk and like swap that out, right? So even for the same operation, if you were going to run out of memory in Pandas, Dask can handle a bunch more because of this mechanism, right? So now in this setting, I was running into a lot of issues, but just by changing the engine, this whole SQL cell will now run on Dask, and Dask handles that memory shuffling, so it's able to pull it through. And because my result set is smaller than those intermediate tables that were had memory issues, now I can like perform that operation with a bit of that finagling, and then all that's done by Dask, and then just collect the results and keep it, and then save it in a Parquet. So this is how we change engine in Fugue. So Fugue SQL will by default run on Panda. There's a Pandas hidden in there, and then you can do Spark or you can do Dask. Something also interesting is if you see my CPU here and you see it's at 400%. So I just started running this notebook before this session. And the reason this is like this is because the Kaggle machine is actually 4 cores. But by default, Pandas only uses one. So it's such a waste of resources. And that's true in general, right? Your laptop is likely a 4 core machine, if not more. And if you're just using pandas to work with on things, you normally are just using 1 core. And Dask is the solution to take advantage of the cores that are also available. Spark also has local mode where it can also take care of those other cores, so you can parallelize your task. Uh, Second thing, just the slight note, since we used yield up here, yield, we can now use the data frames inside, right? And this products is the one that's cached in a file. but FugueSQL knows where to retrieve it. And same with the programming interface. This is also an option. It will know where to retrieve that file for this operation. Uh, just some slight note, when we work with distributed computing, we normally work with Parquet files. For those who are not familiar with Parquet, Parquet is just preferable to CSV for big data. Number one, Parquet is smaller in general because of compression. So normally your data will be around 30%, like there will be a 70% reduction. So it'll be 30% the size of what the CSV was. Number two, it holds schema by default. So you won't have that problem of like you load in a CSV and maybe you did a comparison with an integer, but it was loaded in as a string and you get an error. No, a Parquet holds schema. Number three, it's partition friendly. So by default, when you have a Parquet that you are um, uh, writing out, it will write it in multiple partitions. And then that allows you to parallelize the process of loading it in, right? So as a simple example, if we have a Parquet that's split among 4 files, then we can load each one of those with one core. And then, um, yeah, I'll explain that. So uh, the question here is, what do you mean by column-based versus row-based? So for I believe CSV is row-based, but there are file storage types that are row-based, meaning that, for example, it's like if you want to retrieve data, you have to retrieve the full row, right? Uh, like even if you want like 5 out of the 10 columns, you have to retrieve the full row for that data. So big data tends to benefit from column based, where like maybe the file has 100 columns, I only need 5. So it's faster to just load in those 5 columns, right? Now, if you're loading in the whole data set, it kind of doesn't make a difference, right? It's like I have to load in the whole thing anyway. But if you use something like Spark, Spark can, if you say Spark load this file and then grab these columns and then do this operation, I believe Spark has optimizations that allow it to go into the Parquet, filter out based on uh, what it needs, and that results in speed ups, right? Because if you have 100 columns, you only need to get the 5 columns, right? And then you can work with that. But it's just a matter of which way you're optimizing for. Maybe sometimes you really want the full records. So like I think Avro is row based. I'm not 100% sure, but Avro would be the comparison here, where it's like, can I get Jerry's record in the set of 100 million records, right? And you would have to get the whole row. If you want the whole row, then Avro would be faster than Parquet because Parquet still needs all the columns. Yes, Brian's right. I'll read it for the chat just so the video. Brian said, if you want to pull the average value in a column-based system can calculate it by just accessing the column. A row-based system would have to pull the full rows and then perform the calculation. Yes, that's well said.
Yeah, and that's the thing that you can design your system for. If you know that your data set is mostly going to be used to pull an individual's data, like pulling account information when a user logs in, then you would, if you have the choice, do row-based. But if you're specifically generating a data set for aggregation purposes and analytics, likely column-based would be more efficient.
Yeah, and that this extends to not just the file types, but also like data storage, right? Like as in like databases like SQL Server, those tend to be OLTP systems, which are row-based. But the warehouses, right, like AWS Redshift, Snowflake, those are more column-based, right? Because you want to perform aggregations more on those. So those are the OLAP, like online analytical processing, I think, versus online transactional processing. I'm not 100% sure, but
And then you get fun things like table-based, which is not really either.
yeah. Okay, so let's move on. And we have here, I'm trying to get the top 20 products. These are just, I won't go into too much detail anymore for the sake of time, but we're just using those other plots that we defined above. We just have this order by. Here we have frequency of what are the top 20 product orders. Bananas are number one. Bag of organic bananas is number two. Strawberries is number 3. In general, it's all fruits in the top 20, all perishables. Number of occurrences in each aisle. Fresh fruits obviously became number 1 here, and then vegetables, packaged vegetables. Um, these are all perishables too. And then department distribution of departments. I don't I don't know why it's. Maybe this will be easier if I. Okay, distribution of departments. Number 1 is produce, big chunk. Number 2, dairy, eggs, and then snacks, beverages. We don't really care too much. And then now uh, to introduce partitions, right? So in distributed computing, a partition is basically a logical grouping. This is how the Dask architecture works, right? Where you have a Dask data frame, and it's a collection of smaller Pandas data frames. So here in this example, there's a Pandas data frame that holds all the January 2016 data, and another data frame that contains all the February 2016 data, and so on. And when you perform an operation, what Dask does is it will map the operation to each partition, right? So as long as a partition contains like uh is like self-contained, meaning that it doesn't like this January data does not need to know a lot about the February data, right? So as long as your partitions are self-contained, then you can really benefit from parallelizing your tasks in a distributed setting, right? Because you can just perform that operation on that individual partition. And I have a link to this blog post here, which is really good. I got these images from there. In general, we want partitions to be equal, right? And this is because if you think of a partition as living in a worker, then this means that all our workers are working the same amount, right? But if, for example, January 2016 had insane amount of data compared to February and March, what happens here is that the worker that holds this partition will have to uh, spend more effort, right? And these guys are not fully used. Then we also have inefficient scheduling, right? So if we have 2 executors and executor 1 got 2 partitions, this is obviously inefficient because what happens is we're going to run this and executor 1 will do partition 1 first, executor 2 will do partition 3, and then executor 2 has nothing to do while executor 1 has to finish this. So in general, you want um, like having a high, but also one thing to note here is that multiple partitions can also live on the same executor. So when choosing a partitioning scheme, ideally you want a high number of partitions so that you get a higher chance of it being evenly distributed. In general, you just want it evenly distributed. And the and that brings us to data shuffling. So let's say we had the data above where we had some kind of time-based data, right? And we decided that partition 1 will contain January 2016, partition 2 will be February 2016, and partition 3 will be March 2016. And let's say they each lived on one executor. But then what happens if I needed to do a group by on maybe a user level, right? I wanted to say what's the mean number of uh, items that this user bought, right? Even though now I have to go from the time base to another kind of partitioning scheme. And in order to achieve that partitioning scheme, I need to move data around. And this means, and you don't have to worry about this because Spark and Dask will handle this for you. But in general, it's just good to be uh, like aware of shuffles are bottlenecks. And of course, it's inevitable that we need to shuffle data eventually. But um, in general, when you do shuffle, you want to do ideally as many operations in that configuration as possible before you have to reshuffle into another partitioning scheme, right? So over here, um, if we went to like by user for all of a sudden, now we'd have to shuffle the data such that all the data for a specific user will live in one executor, right? And then, so in general, shuffles are unavoidable, but uh, but they are bottlenecks, right? So let me give there's just one uh there was just one point of confusion last time I gave this workshop. So there are some operations that, for example, a group by mean for a user does not require a shuffle, right? Because I can get the mean of a user even if the data lives across different partitions, right? If if this is time based and I have some of user A's data here and some of user A's data here and some of user A's data here, I can still get the mean by doing kind of like a map reduce, right? Where like I just do the mean here, mean in each executor, and then I aggregate it later, right? But there are some operations that cannot be done this way, right? And a median is a good example, right? If I need to get the median for like the for user A, I need to collect all of users A's data into one executor to accurately know the median. I just want to make sure that that concept is clear. So
And
the
so
first one is
that's
the map.
analogous to structuring your query such that you front load all of your operations that can be done within the partition, and then as late as possible in your query, uh, putting any operations that then have to mix across the partitions. Yeah.
Yes, 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 for sure. Um, so aggregates can be done, like aggregates can be done, sometimes can be done like without shuffling, but and it Spark and Dask will intelligently do that, but sometimes you really need to shuffle. And here's our example. We so for each customer, maybe customer A has 10 Instacart orders, and we're just interested in getting the median basket size for that for each customer, right? So we want to do this across all customers. So we're gonna make a new function here. It's gonna take in a data frame and output a data frame, and then it's gonna just return the user ID that's associated with it, and then the median for that user ID. So by the time a data frame already comes into this get basket size median, it only contains one user already. It's already partitioned. And then this schema here is enforced by Fugue. So Fugue builds a directed acyclic graph of all of the operations. Same thing with the distributed computing framework. Spark and Dask also build DAGs under the hood. Fugue also builds a DAGs and checks the schema in, schema out, just to make sure that if there are errors, you don't have like a 4-hour job, ideally, before the error uh, takes effect and you lose all the work that has been done, right? So Fugue will read the schema hint, and there's also a schema decorator that's like this, or it'll take in a string. So there's two ways to do it, but this schema is enforced. Oops. I see questions in the chat. Yes. So the chat Jerry said aggregate means to get a grand mean, but median requires a ranking. So median um, requires all of the data for that user to be in that one partition. Yeah. So we have 206,000 users, and it's not productive to run it on all of them. So we'll take a sample of 50,000, and we take a sample by creating this user ID table, and then we do select distinct user ID from orders, and then we sample is a Fugue keyword. So now we sample. We use the Jinja templating here to put in 50,000. So we sample 50,000 rows seed one from user ID from this table. And then we yield this. So user IDs is now available. This next section, so we got questions before. How do you productionize like from a notebook to like a Python script? And this is how we do it. So we wrap the query into like a string, and then we have this FSQL function, and we put in the query, and then we do dot run. And over here, again, this FSQL, we can control the execution engine. By default, it's Pandas. I just want to walk you through the query, so it's going to help if we have a bit of syntax highlighting. So here we create the basket size. The basket size is just a count. How many items did this order have, right? And then we just get the orders from we get the user ID, order ID. This is joined to the sampled 50,000 that we have earlier. So this is already this is already the sampled size. And then we just join this basket size uh, to each order, right? And because we have the shuffle that happens, and we have, even for 50,000 users, let's assume we have 1/4 of the data, we still have 8 million records here. It's still going to take quite a while. So this operation took 552 seconds, right? And then now we're going to bring the same query into Spark. Oops. And we're just going to do this by passing Spark. Again, this is the equivalent if we have a SQL query of doing just this. This would be the same thing. And now, for the same query that was run on Spark, it ran in 90 seconds. So we're comparing 552 seconds with 90 seconds. In general, there should be like a 4x speedup just because we go from 1 core to 4 core. You may notice that this is more than a 4x speedup. This is because Spark has an optimizer. The engine has an optimizer itself. So even if you just write like Python Spark code, it's going to optimize that code. And like similar to like SQL, if you query, there's like an optimizer, like it can intelligently grab columns. Spark is the same way. And like what I said earlier, if our file is a parquet, Spark can intelligently go into that parquet, only use the partitions that are relevant, and then like more efficiently do the task, right? And Dask has some optimizations too, but from what I know, Spark has like is way more optimized, but I may be wrong. So here we've shown that the important thing, none of the SQL had to change, right? The SQL is the logic. The logic is decoupled from execution and entirely separate. So it's all about maintaining your SQL and your logic to be agnostic to the data size. And here is where we just change the engine once we need to with one line of code change, right? Uh, Next, the last two are just a bit of just showing more of what. Well, there's one more concept here actually. So here we're gonna get the top 5 products for each user. In this section, um, so all we want to do is do a count. Like user A used Instacart 10 times. Like which items did he order the most among those 10 times? So the first is we're gonna again join to our sampled users with this user ID. Uh, Next week, do a count for each product. It's pretty straightforward. And then we do we join. Sorry, we do this. All there's a join here, but all you need to know is that we have user ID, product name, and the count in this temp df. And then we're gonna join this temp df to this second data frame, which is the maximum number of orders as n orders. So here's the output, right? You're gonna see user ID, the product name, how many times they got it, and the number of orders in total. And then the next part is a Fugue specific keyword where I am taking 5 rows for each user ID, pre-sort count descending, right? So I want the I want to sort the number of the count, and then I get the top 5 rows so that I can end up with the top 5 products for each user. and then save into this parquet, print 15 rows. Same thing, you have five, five. So we're printing five products for each user, and then the total number of orders. And there is something interesting in this section, right? Because over here you're gonna see persist. And in distributed computing, what happens is the DAG is created, but nothing is executed until there's an action that forces the execution of that directed acyclic graph. So things that force actions are like printing, saving, showing, like those kinds of things. Those are the ones that actually force the computation to happen. So while you're coding in Spark or Dask, nothing is actually happening until that data is needed. Now there is an issue though, right? So here is like an example DAG that's being built. You're gonna see that R10, R11, R12 need R00. There is something with Spark that as you calculate R10, as you calculate R11 and R12, this R00 gets calculated 3 times, right? And the way to avoid that is by persisting this, so you don't redo that calculation. Uh, so here we have the date. So persist is a keyword added to FugueSQL. So now we can persist this data frame to prevent recomputation. And then next time that, so as R10 is calculated, this gets persisted, R00 gets persisted, and as R11 and R12 need it, it's available to them. So this is entirely different from Pandas. Pandas, you do it once, it's already there in memory. In distributed computing, you need to explicitly persist that or cache something, like I need this, so that it can be available for future runs. Fugue has some like because there's a DAG in Fugue, Fugue can intelligently persist based if it is used in future computations also. But in general, we added the persist keyword there. Then the next thing is just because I gave this workshop for data analysts, I tried to do like a data, like a softer machine learning kind of thing, right? So here we're gonna have a Python function, and this is gonna fit the trend line, uh, degree 1. So it's just here y equals mx plus b. M is the slope, b is the intercept. Here we are just interested in like, so there are users who are who reorder this. If you reorder the same amount each time, then your trend will be 0, right? But we are interested in the users who seem to be reordering more all of a sudden, or seem to be reordering less, right? And maybe there's something there. So we have in general, the important part here is that we're gonna take 10 rows pre-partitioned by the user ID, pre-sort by the order number. So this means get me the last 10 order numbers descending, and we'll keep that. And then we perform this Python function, reorder trend, on that user ID. So we partition by the user ID, and then we use this reorder trend. And then we can yield the file. So the reorder rate will look something like this. So we have one user, and we got the last 10 order numbers, and the reorder rate fluctuates between the order number, but we're fitting a line through it. So now our trend will look something like this, where we have the numbers won't vary too much. These shouldn't be wild swings. And then from there we can select star from trend stats, order by trend decreasing or increasing to get who are the ones who are reordering more all of a sudden, and those are these guys. Who are the ones reordering less? Like they used to reorder more and then now it's going down. And then these are our bottom 10. The last thing I want to show you is I need to. I tried to run this before, but it wasn't fully. I tried to get this to work just before this call, but it wasn't fully working. But I wanted to show the comparison between SQL and the Python interface. So here we have the top 5 products for each user. and I'm gonna paste this code. This is the SQL side. This is the Python side. So you're gonna notice that um, here we have, this is the programming interface. This is the Spark execution engine. Again, if this is not filled, it will use Pandas by default. We can also do the Dask execution engine, and it will run on Dask everything inside here, right? So if you have data frames that are in Pandas, they will be converted to Spark. Uh, if they are data frames, if you want to use Dask, they'll be converted to Dask. In general, all of the like all of this data frame, all of the code here is agnostic to Pandas or Spark or Dask. It's all about there are some few keywords like partition and transform, but in general, this is again this will just be the logic, and you choose your execution engine later. We also have this helper function that is written in Pandas. So we have Pandas in, Pandas out. But I wanted to show an example of a helper function that is written in just pure Python, right? So we don't even need Pandas. And here we're going to take in a data frame with this type annotation. Type annotations are enforced also. Or, I mean, if it is not that type, it will be converted to that type. This output type is enforced, so it checks to see if that type is actually true, and that's why we have to use this yield. So this function will take in a data frame and n, and let's say n is 5. It means that it will get the fifth record from the top, right? So for row in df, if n is equal to 0, we yield that row. Otherwise, n equals n minus 1. So if you say get me the nth, and this is how you would invoke it, you partition by, you pre-sort, and then you transform with this function, and then you provide the parameter, right? Um, and you say n is 0, and n 0, you just get me the top, the min, or the max. Depends on how you sort it. If you say 1 or 2, then it's like the first from the max or min. If it's 2, the second from the min or the max. Um, and then the SQL that you saw previously gets mapped to the Python interface, right? They are the same abstraction layer. So now you see the partition, you see the take. These are the same commands as here with pre-partition, because SQL already has partition, and then take, right? The save over here, we have data frame.save, mode is equal to overwrite. It's the same here. Show 15, same as the print 15 rows. So there's also a programming interface. Um, in general, though, we see like better feedback with the SQL side, especially because SQL and you can combine like Python functions inside that SQL. So people who are like, they know Python but not necessarily like Pandas, it's kind of a good fit where you can just use what you know and build your end-to-end compute workflows. And with that, that's the end of my content. Um, I just have I just want to say that if you're interested in contributing, Fugue is open source. You can talk to me. You can join our Slack channel here. There's a lot of work to be done. If you're interested, you can just touch base with me, and we can talk about it. And with that, that's the end of my presentation. Thank you all for coming. I'll stop sharing my screen and open to questions.
Well, thank you so much, Kevin. As we wait for some questions to potentially come in, certainly interesting having an abstraction layer on uh, just the scale that you need. Because definitely, if you're trying to run Spark locally, you absolutely can. But if your test data set is super small, you don't need that. It's really nice just having knowing that you're only going to use uh, the capabilities that you would have with pandas, and then you can scale it up to data centers without having to change the same code. Very interesting to see.
Yeah, so one of the main use cases is indeed because of how hard it is to test on Spark. Spark on local takes like 4 or 5 minutes to spin up, and even just like those unit tests takes forever to run. So one of the use cases is like, okay, let's test on Pandas first. And because the abstraction layer is there and the pandas behavior is guaranteed to match the Spark behavior, if my unit test passes on pandas, it'll pass on Spark. So then I can just use Spark to handle the big data workflows and like scale it out when I need. So it's also cost saving in a way, because you, instead of like just letting it fail in production, you can catch things earlier by testing in pandas, especially because the functions used can be written in native Python also. So it makes it very easy to test.
Now, I'm curious for the specifically for the Spark and Dask setups, because pandas can be run locally. You don't, as long as it's installed, you don't really need to do anything else. When you move this into a data center, where what configuration do you have is made available? Is that managed by Fugue to say when I'm
Uh,
in the data center, you have access to the following machines, or are you just relying on the configuration that exists with your local implementation of Spark on that machine to handle those connections?
yeah, I'll share my screen again to answer that. So here in the README, there is a you can make so here we have a Spark session that we're making, and these are the configurations, right? Where you say I have this many cores, I want like this many RAM or whatever, and you create that. You can pass that in the Spark execution engine, and then you can insert this Spark execution engine in your workflow. So for the programming API, this exists. I believe in SQL it can be done. What you can do is you configure it this way, and I think I'm more sure about Spark, that when you call Spark, it just gets whatever session is alive. So you would get the session that is alive. But also on the so you can control this programmatically, and then you can when you do it on the SQL side, or you can feed it into the API, it will get the right session. I don't have it on me, but I know Dask has the cluster that you set up. The cluster can also be configured in the same way and passed to the Dask execution engine. So there is that availability. But in terms of actually like configuration beyond this, like actual the networking and like the cluster management, no, that's on the platform that you would use, whether that be like Databricks, right, or like Saturn Cloud for Dask.